Hello and welcome to Friday's edition of Cracking the Cryptic, and what should be a very special puzzle today on the birthday of one of the constructors. So this puzzle on screen is called The River. We've had this recommended to us a lot actually, and having read the rules I can sort of understand why. It sounds completely and utterly, well, sort of a cross between ridiculous and unimaginably brilliant, but it's by Jacob and Woofers I can never say Woofers for Gig's name. I don't know whether I'm meant to say Woofer ZFG or something, but I like to call them Woofers for Gig. And anyway, it's Woofers for Gig's birthday today, so we did actually have a very nice email, I should add, from Jacob, his co-constructor, saying that since they both found Sudoku in this channel, they've really formed a great friendship, and you know, it's just wonderful to hear these stories. So Woofers for Gig, I hope you have a brilliant birthday with, of course, plenty of cake, and I should also say a very happy birthday to another young lady, Alison Hebrard, who today, it's your birthday too. I think you're over in the States, but I can't remember exactly where. But Alison, I hope you have a great birthday as well. Now, in other news, lots and lots going on around the channel today. Earlier on, I released on the channel, available to everybody, this incredible puzzle by Phistomefel. It's his April Fool. Check that video out. I don't know when I'm solving the puzzle it's an April Fool. Even at the end of the video, I'm not wholly convinced it's an April Fool, but it was only after the video that I went back and realised Phistomefel released it on the 1st of April that I understood the nature of the joke. And yeah, it's an incredible puzzle with an incredible rule set, and you know, just a great prank by one of the greatest minds on the planet. So I definitely recommend that video to you. Also, of course, right now, yeah, 4 o'clock today, Kinlux's new Sudoku hunt went live over on Patreon, so I hope you're all having a go at that. You definitely should. It is a wonderful series of puzzles, not easy, as I said yesterday, but definitely worth checking out. Now, I don't think I've got any other news. I probably am meant to say something else, but I can't remember what it was. So let me read you the rules of The River. With a small warning today, I do have to go and catch a train later to go for lunch in London. So maybe I'll see one or two of you there. You never know. But that might mean I have to pause the video if it gets too close to my train time, which is about 40 minutes away, so I've not left myself enough time to do this at all, I've no doubt. Okay, here we go. Place the digits 1 to 9 once each in every row, column and region. Regions must be determined by the solver, and each region is an orthogonally connected group of 9 cells. Regions cannot overlap, so that means we have to discover where the regions are in this puzzle. So that could be a region, for example. That's 9 cells, they're orthogonally connected. Orthogonally just means connected by a long edge. So those 2 cells are not orthogonally connected, but those 2 are. Right, let's get rid of all the colours. Now, this is where it gets complicated, and I think this is why it's called The River. Digits on the blue line have an equal sum n within each region it passes through. If the line passes through the same region more than once, each individual segment of the line within that region sums to n separately. So this is a region sum line, which is absolutely wonderful, and I love region sum lines puzzles, except this puzzle has no regions at all, and we're going to have to work out where they are. So I think I'm going to just start with a small example here. Let's try and get our heads around this. So let's imagine that n was 8. Now if n was 8, well that... Oh, actually, right, okay, I've now seen n can't be 8. But anyway, let's stick with my idea that n is 8. So let's say this was a 2 and this was a 6 on the line. Then we would know that, no, that's not going to be a region. That's going to have to be a dividing line, and that's going to have to be a dividing line. Because within each region the line passes through, it collects digits on its route through a region that sum always to n. So if n is 8, these 2 would sum to 8, and therefore we'd have to exit the region. And then these 2 cells would have to add up to 8. Or actually, no, that's not true. It could be 3 cells. Oh, and I've put a 2 in this row, so this is all horrible. Let's switch that around. This can't be an 8 on its own because of the 8 here. But now we could have 3 cells adding to 8, which would have to be those 3 cells, and then we'd have to exit here again. So it's a really interesting idea, but I'm not entirely sure how we're going to solve it, but I suppose that's the point. Do have a go. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. Now, come on, Simon. You're going to have to use your brain today. Oh yeah, now, so when I was just putting, when I had my idea that in the example that n was 8, I realised there's a 9 on the line. So if there's a 9 on the line, n clearly has to be at least 9. Now, it would actually be very handy, and I could, right. It would be, I was about to say, it would be very handy if we could prove n was greater than 9, because then we would know as we came in from the edges, we had to have at least 2 digits each time, because if n is greater than 9, we know it must be at least 2 digits to make up a total of 10 or higher. And I can do that, because if n was 9, then you'd have to put a region boundary there, and then this 7 would have to have either double 1 accompanying it, well that won't work, that's going to break the rules of Sudoku, or a 2, and you can't put 2 there because there's a 2 beneath it. So that actually looks quite deliberate on the part of Jacob and Rufus Vergig. So that means that we are, so that means these 2 cells at least are in the same region, doesn't it? That's what it means. And it means these 2 cells at least are in the same region, because we know n is at least 10. Now, I'm just having a strange thought here. It's not possible, is it, that n is 45 here? This is some sort of quasi-April Fool. And the reason I'm asking that is if you look at the top of this grid, there is an awful lot of river. I mean, this is one prolific river. This is the sort of Zambezi of Sudoku rivers. In fact, that looks a bit like a crocodile. And having whitewater rafted in the Zambezi, I can tell you that there are definitely crocodiles in it. Now, yeah, so what I'm wondering is, I mean, it's almost, actually, I don't know if you could do that, but could you do that as a region? No, actually, that wouldn't work either. It's quite tricky. Oh, okay. Actually, maybe I'm wrong about this then. Maybe it's not 45 because you can't keep a 9-cell region on the line for long enough. No, you can. That would be a 9-cell region. And that would be a legitimate region to draw. That's 9 orthogonally connected cells. So then you'd have to do these. No, it doesn't. I don't think it works in terms of the way that you map from region to region. How many cells in the grid are not on this line? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 are not right. Okay, so that tells us it's not 45. Because if it was 45, we should have a mod 9 number of cells left over at the end, surely. Because each time the line hits a region, it must collect 9 cells from that region and then move into the next region where it must collect 9 cells again. If n's 45, that's right. So it's not 45, and it's not an April Fool, even though it is still April. I had to check that. That shows how useless I am at what day it is. Now, so right, what do we know exactly? We know that n is at least 10, and we know that it's not 45. Now, that I do realise there is a lot of scope between those numbers. But what we also know, Oh, where's my colouring up there gone? I had some colouring up here. What we also know, yeah, how do you get this region here? It's gonna appear in the grid somehow. How does it have even one cell that is not on the line? And the reason I ask that is surely if every cell in the yellow region is on the line, then no matter how many times that line dips in and out of that region, it's picking up n digits each time, and that means that n must divide into 45 because of the secret. I realise I sort of elided over the secret. People might have wondered why I was talking about 45. I was talking about 45 because that's the sum of the digits 1 to 9. So every complete region in this puzzle will contain digits that sum to 45. Now, yeah, so if we can prove that yellow never gets... So yellow can't pick this square, because to get to this square it would be 10 cells, wouldn't it? Even if we went the most efficient path. That one's surely too far away. 2, 3, 4, yeah, that's too far away. Oh, that one's not on a line. And literally it is a 1 as well, so this 1 is not on a line. And that is Bobbins-worthy. I don't believe it. Ah. Oh no, hang on, that wouldn't work. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, that doesn't work. So it's got to be some shuffle down these two columns. Oh, that's very annoying. If this cell had been on a line, then I think we could have said with certainty that the yellow region always stays on a line, and that would have meant that n would have to divide into 45 exactly, and because n is at least 10, that means n is not 45, it means n is 15. So I think n is going to be 15 unless this is in yellow. Now if this is in yellow, there would be a cell summing to 1 that is not on the line, and that would mean that the yellow cells would sum to 44 in the region, and so n would have to divide into 44, so n's probably 11 then, or 22, but probably 11. Oh, right, hang on, I'm starting to understand this. Right, so hang on. In order to get this to this, if I have to do that and I always have to pick up 2 cells each time, I can't just come straight down the column. And the reason I can't come straight down the column is that this, you can see as the line moved through the region here, it only picks up this cell. Yeah, it'll be clearer if I draw a line around this, like this. So you can see as the line moves through the 9, it picks the 7 up in the region and then exits again. Well, this would have to be n, which we know is at least 10. So that doesn't work at all. This is absolute nonsense. And that might be how we prove that this can't be yellow. Yes, we can't come here. That's the first conclusion. We simply cannot come here, because if we come here, the only way of getting to 1 in 9 cells is with a straight line, which doesn't work. So we must drop down. And we can't drop down to here, because that is not efficient enough, is it? However I do this, I'm going to take 10 cells, I'm sure. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so we've got to take that cell in order to get to yellow. And then we have to be efficient, so we have to take this cell, because we need 2 cells on the line before we exit. And now we've had 4, 5, so we have to be... Yeah, this doesn't work. You have to drop down, and again, we get the same problem here that we got the other way. We get this as the region, but this is only 1 cell. The line goes from out of yellow to out of yellow. So this has to sum up to n, which we know is at least 10. Same is true there, actually. Not true here. but it is true in these two cells. It doesn't work. Right, so this is huge. This is a huge deduction, because now, let me just check this logic again. If all the cells of yellow are on the line, which they must now be, then we know that the sum of the digits on the line in yellow is 45. Therefore, n, which must be how many cells the line picks up each time it enters yellow, must be a divider of 45. That is true. That's true. And we know n is at least 10. And there's no other dividers apart from 15, are there? No. No. What are the prime factors of 45? 3, 3, and 5. Yeah. So yes. Okay. So this is so n is 15. Now if n is 15, I can draw that line segment in, because those two cells add up to 16, and that won't work. So now, what's the task? Well, the task is, this is where it's going to get very tricky, actually, because I want to know whether the 7 is yellow now. The 9 has to be in the same region as that cell, because we have to get to 15. The 9 can't take that cell, because that would be, these 3 cells would have to sum up to 6, and they can't because 3 is not available. So right, oh, this is lovely. Right, so this means that along this stretch of line, these 4 cells, we have to include 2 15 sums, because 1 15 sum is impossible, and therefore it must split into dominoes. So yellow is not the same as this digit. So I'll redify those two, and that probably means that this is yellow. And this square must surely now be red. Yeah, if this square was not red, given that this square is definitely not red because there has to be a junction here between the borders, you could never connect red to red. So that's got to be red. Let's put in the boundary there. Right, oh, I see maths helps us, doesn't it? How do you make 15 from those 2 digits if one of them's a 9? Well, that's a 6. I suppose that's got to be a 7 and an 8 now, because it can't be 6, 9 and must add to 15. Right, now 7 is not yellow, because if 7 was yellow, it would repeat in its region. This is a heck of a clever puzzle. What an idea to have, that you could make a region sum line puzzle without regions. Right, at least those 2 cells must be... Oh, no. Right, I love this. I love this. It's so pretty. So, I'm not speaking about the chromaticness of the puzzle now. I'm talking about the logic. This is now not yellow, but yellow still has to get out of the top left of the grid. So yellow's got to drip down here. And that means that purple is only 2 cells, and one of them's a 7, so that's an 8, and that fixes the 8, 7 at the top. So this, right, yellow is at least 2 cells now to add up to 15, so that now is yellow. We get a sort of U pentomino out of the top of the grid. This purple has to get out, so that must take at least 2 cells, so that's got to be there. Now what? Okay, now I'm stuck. Can we go further? Yeah, I can do something with these 2 cells, I think, because those 2 cells have to sum to 15. So this square's clearly got to be a 6, and that's got to be a 9. Because this could be neither 8, 7 nor 9, obviously, because of Sudoku. So the only digit left for a 2-cell sum to 15 is a 6. Oh, right. Now, am I going to be correct about this digit? what I'm thinking is yellow has already used up 30 of its 45. So so whatever this digit is, it needs to be part of a quintuple, taking all the other digits in the yellow region, because if it isn't, it will never reach the sum of 45. So that... but the problem is we don't know which way round it goes. So this digit, which is a 1, 2, 3, 4 or 5 by Sudoku, has to be part of a 1, 2, 3, 4, 5 quintuple to get to 15. 5. No, it can't take that digit. I don't know. I'm not sure which way it goes. Right, purple. This purple is not a domino, because it needs to add to 15. It can't be 6, 9. It can't be 8, 7. So purple has to come. Oh, this is so clever. Purple has to come here, which means red has to get out. So those squares become redified. Now, how could this now not be purple? If this is not purple, how do you connect purple to here with putting a 9-cell blue region in the middle of it? You can't. So that's got to be purple. 1, 2, 3, 4, 5, 6. Okay. So, right. So this is a very specific... Yeah, okay. I'm not sure if I'm right about what I'm about to say. I think I am. These 3 digits here, none of them individually can be higher than a 6. And that's because this 9 obviously sees the whole of those 3, and 8, 7 sees the whole of these 3. And this actually sees 6, 8, 7 and 9. So if none of those can be higher than a 6, and there are 3-digit sum to 15, they must be a 4, 5, 6 triple. This is really, really brilliant. So now the 6 goes here by Sudoku. And now I've got... No, oh no, I haven't quite got it. No. Well, I've got a similar thing going on to this cell. I've got cells here that sum to 30, yet there is another cell in purple on the line. So this purple needs to take every other purple cell on its line segment, in order to get to a count of 15. And that cell is a 1, 2, 3 or a 9. And no, it's not 9, because there's a 9 here. But it's going to have to be a 9, 1, 2, 3 quadruple on the line. And it has to connect. Oh, hang on. Is this the same here? I'm getting a bit confused here, but I think that this sort of thing is happening a lot. So this enters red, and these 2 digits here have to be quite low. They can't be... 9 has already appeared in red, and they can't be 8, 7 or 6. So the maximum size of those 2 digits is a 5, 4 pair. 5 plus 4 plus 3 is still not enough to get you to 15, so that's got to be red. And 5 plus 4 plus 3 plus 2 is still not enough to get you to 15, so that square's got to be red. Yeah, oh, yeah, I understand. I was thinking, but what happens to the 8 and the 7 in red? But that... because you're never going to be able to get to a none-line cell from here with orthogonal collections. So I reckon... Oh no, I was going to say those 2 are going to be the 8, 7. How is this going to... No, maybe these 2 are the 8, 7 in red. I haven't quite got my head around it, but these cells definitely are... Those have got to be... Well, this has got to be part of a 1, 2, 3... 4, 5 quintuple. And then this cell, which is the next cell on the line, is not red. So that needs a new colour. We will make that... I don't want to use orange. I could use green. Grey? I think I'll use grey. And that's therefore got to be grey. Yes, and that this is correct. So now, how is red going to grow? Red has to come here. Oh no, I'm not correct. I was going to say these two, but that doesn't. That I don't think that's necessarily true. It could be this one. Oh bother. Okay, well, let's look at this digit then. That must be grey. Again, it's the same logic as before. If we try and make this anything other than grey, then we've got to make blue 9 cells somehow, and then ring 9 cells to in 9 cells to connect the grey. That's just never going to work. So this is definitely grey. 1, 2. So that's grey in the corner. And I know that's not a song, but that should be a song. And the reason it's grey is that if it's not grey, these two could add to 15, but this cell individually would have to add to 15 because it then re-enters grey again. So this is does that mean this is a 4-cell string or a 5-cell string? And if it's a 5-cell string, we know this would be a 1, 2, 3, 4, 5 quintuple. And we wouldn't be able to put 9 in the row. Aha! So there's a 9 in here. This is a quadruple, therefore, because the other 3 cells are going to have to be a 1, 2, 3 triple, which we can therefore write in. 3. And this is a new colour. Oh, yeah, beautiful. This is the new colour, but we know that this is red. So given that this can't be a 15 on its own, it must join to the red, and therefore that is the 7 and 8 that completes the red region. Oh, I absolutely love this. Jacob and Woofers for Gig, you need to do another of these puzzles. I can tell you that already, because this has got legs. This is it's so interesting. Now, yeah. Now. Yes. It's beautiful. So purple, we've already looked at this. We've got those squares adding up to 30. We've just got this square, which can't be a 15 on its own, so it's purple. But that means that these 4 squares have to be the 1, 2, 3, 9 in purple to complete the purple region. So all of that gets purplified. This is 1, 2, 3. This is 9. Purple is now finished. We can ring that with ringage. And where does the thing go here? So it exits purple there. So this is a new region here. Now, is this a new colour or could it be yellow? And the answer to that, I'm not sure. I'm not sure immediately. Can I get away with blue? I don't really like blue. I get blue against the blue line. I'll use red because... Oh no, I could use orange now. Orange is safe because it's probably not going to touch this. So this is orange and this is orange, but we have to bear in mind that orange could be yellow here. Again, the same logic. That's going to have to be orange to allow the connection to happen. Now that's huge, surely, because now how could this possibly be yellow? Because if this is yellow, not only is that square going to have to be, because we know yellow's only got one more 15 sum from it, and these 3 digits cannot be all in the same sum to 15. 1, 2, 3, 4, 5, 6, 7, 8. You need an 8-cell 15 region, which won't work. So this is a new region. But we don't know, or do we, whether can this be a 2-cell sum? It would have to be a 7, 8. Which would have to be this being 7, this being 8. And very, very annoyingly, that looks like it could work. So I'm doing dreadfully in terms of finishing this puzzle in my 40 minutes. I've nearly had the 40 minutes. How could I nearly have had 40 minutes? Good grief. Okay. So, calm down and try and do a bit more. We can. Right, well I know this is part of a quintuple on the line. So this could be yellow, this could be yellow, but then it's still necessary for the next 3 cells to be yellow. I see, I've got it right. So now we know this is part of a quintuple. Well, the quintuple stops here because this we know is orange, and that forces the quintuple to have to take this cell. That is a quintuple. This is a 1, 2, 3, 4, 5 quintuple, and that's not 2. So this, so now yellow is finished. And as we re-enter orange here, we must take, well, we must take 2 more cells, at least. No, exactly, because 5 plus a single-digit number is not going to get you to 15. So we know it's got to be 3 cells, but it can't be 4, because those 4 cells would add up to, well, these 2 would add up to 13. Those would have to be double 1 in the same region, which won't work. So this is a new colour that shall be, oh, bobbins, do you think that's going to touch that? It's possible, isn't it? How do I always get myself in this pickle? I'm going to make this black. I don't really like the look of black. I'm going to make this. These are the decisions. Yellow is probably safe, isn't it? I'll make it yellow. So it's got to be at least 2 cells. This could be a 7. I think at least. So those 2 squares add up to 10. Oh no, I know where to look here. These 2 squares add up to 15. And this one can't be 9 or 6. We know we're looking at a 7-8 pair, and that's a 7. So that's 8, that's 7. Ah, now that's not... Okay, so yellow's got to go 1 more, at least, because these 2 squares... Well, this square on its own couldn't have been a 7. So, now if yellow was 3 more cells, this would be yellow. Oh, this is very interesting, actually. You can't do that. So it's not... In theory... You can make 3 cells add up to 7 in Sudoku using 1, 2 and 4, but not in this puzzle with this geometry, because the necessary implication of this diagonal connection is that this square would need to be yellow in order to allow connectivity. You make this something else, you can't connect the yellow to the yellow. Putting a 9-cell region here as a barrier, but just won't, the count will never work. So this being yellow means that the line has got 4 cells before it's exited. So we'd have 4 cells adding to 7, which won't work. So actually, this is incapable of being yellow, which means right, okay, so what we've got here is a boundary here. Boundaries here. But we don't know. We don't know. Well, we don't know whether this cell is grey, is the point I think I'm trying to arrive at. I could probably make this green. It's at least 2 cells. If it was 2 cells, it couldn't be 7, 8. So it would need to be 6, 9. Right. These 2 cells sum to 7. Those 2 cells... Ah, that's interesting. Those 2 cells sum to 10 on the line to make this little stretch of line add up to 15. And you can't put 6 in either of them. And you can't put 8 or 7 in them. So they're a 1, 9 pair, and there's a 1 here. So that's a 1, that's a 9. That's not 1 anymore. That's not 1 anymore. That's not 9 anymore. By Sudoku. So, how does this now work? Gosh. That can't be a 2-digit 15 sum, because 9, 8 and 7 have gone from the column. So you could put 6 in there, but you can't accompany it with the 9, and obviously you can't make it an 8, 7. So that's got to be green, which makes the corner green, because this otherwise will be a 1-cell region. Now, 1, 2, 3. Can we keep going up here? And if so, for how far? 1, 2, 3. 1, 2, 3, 4, 5. This is the furthest we could go, and that would be a 1, 2, 3, 4, 5 quintuple, which wouldn't work because that would put too many 1s, 2s, 3s, 4s, and 5s in the column. We'd need this to be a simultaneous 7 and 9, and we don't get Schrödinger cells, not even crazy puzzles like this one. So the furthest this can go 3, 4, 5 is here. So there has to be another region. Right, I think what I'm getting to is because there's another region somewhere up here that's not green. How does that... Oh, that region could be orange. I was about to say it had to come out through here, but I was forgetting, of course, that the region that lives up here in this little cul-de-sac could be orange and just escape through that junction. Okay. Let me think about something else then. This is a boundary from this 5 to this 1 because there's already a 1 in orange. So that is a boundary. So orange can go left to the 2, which is actually what I think it's going to do, or it can drop down here, or it could do both. And if orange takes the 2, it's going to have 3 cells at least on the line segment. But it could... Ooh, actually that's interesting. Let me just think about that. So if this is orange, because we've got 30 there in orange already on line segments that are not this segment, if this was orange, every other digit in the orange region would have to be in this line segment, which would be all 4 digits. So that would become orange. And those, what would those digits be? Those digits would be 3, 4, and 6. So this would be orange. I think that's possible, isn't it? I'm not immediately seeing why that doesn't work. I'm running out of time here. I'm running out of time. I've got 3 minutes before I need to run and get my train. Okay, come on. Let's see if we can make another deduction at least. I'm probably not going to finish it in the next 3 minutes. I think I have to accept that. It was probably foolish of me to even try. So, how can we make more easy deductions here? Indeed, are there any easy deductions to be had here? Maybe I can disprove that this is a domino. How am I going to disprove that this is a domino? I'm going to disprove that because... Oh, I can disprove that. You can't put 9 in here. Yes, there's a 9. The 9 in purple is looking at this cell. So you can't have 9 in either of those. And you can't have 7, 8. We've already said that. So this has got to be at least 3 cells. I'm not sure whether that matters a huge amount, but it does feel... I think every time you get an extra cell in a region, it does feel like a minor breakthrough, doesn't it? So now... Now I think the question we need to ask is green the same as grey? Now, if green and grey were the same, let's just imagine that for a moment. How on earth is that ever going to work? It's not. It's not, and I'll tell you why it's not. Because there has to be something that separates grey from green here, doesn't there? Or is that true or not? I'm just thinking if we just connected... Is that wrong? Or am I going crazy? So if we just made all of this grey. No, the reason that doesn't work actually is that that's all the grey cells. That's all 9 of them. Yet because there's no gap here, there would only be 2 lots of 15 in the region. There needs to be 3 lots of 15. So if this was grey, we would need, and we tried to make this grey. Now, there can't be another region in grey because there's only one cell left to put in grey, and you're never going to get to a count of 3 15s in grey. So you can't connect. The problem is you just can't connect this to this in any way. Because to connect this to this, you need to be taking one of these. Well, you need to be taking this cell actually. But you never can do that because then you're connecting 8 cells in grey together without a break here. So those could add up to 15. These would add up to 15. You've got one more cell to play with that would need to add up to 15, and that won't work. So this is its own colour. We made it green before. And that means that grey is trapped in the corner up here and has to get out. And I realise I've gone over my time limit, but I just want to at least finish on a decent deduction. So now this has to get out. 4, 5, 6. So it's got to come down here. 7, 8, 9. It has to take those 3 cells at least, possibly more. And we'll continue that a bit later on when I'm back from London, hopefully. Anyway, pause now. I'm back. You probably don't realise this, but there's been about 6 hours between when I paused the video just now and when I've just resumed. In that time, I've been to London. I had a very nice lunch with some old friends, and I didn't have any drink. I didn't have anything to drink, so I've got no excuse if my Sudoku is now bad. And I'm trying to remember what I was doing in this puzzle. And it looks like I was highlighting grey cells in this column because I'd worked out that green and grey were not the same. Right, so what? Well, okay, I can see one thing immediately. That cell is definitely now grey, for if it was any other colour, it would be a 1-cell region. So now I've got 8 cells in grey, and actually that's rather beautiful because that cell is now green. How do I know this cell's green? Well, it's only got 2 choices. It's green or grey. But if it's grey, then we'd be saying that that contiguous sequence there would have to sum up to 15. 15 plus another contiguous sequence there is 15, so that's 30. And this cell would have to equal 15 by the secret, because we need the whole of grey to equal 45. And that won't work. I cannot put 15 in this square, so I'm going to put green into this square. And now, yeah, now I know how grey finishes, because I've got 15 here, I've got 15 here, that's 30. So I've got 2 more cells in grey, one of which is off the line. So the second must also be off the line, because if it was on the line, it would have to be a 15 sum again. And the only cell that's available is that one. So these 2 cells sum to 15, and they don't involve a 9, so they are 7 and 8, and there's an 8 here. This puzzle is so clever. Now those cells are therefore 4, 5 and 6 by the power of Sudoku, and 6 is actually, I hope that can be a 6, or I've made a mistake, that can be a 6. So I've got a 4, 5 pair here, which means I've got a 4, 5 pair look in row 2, which means that square is not. So that means I've I think I already knew I had a 3 here if I'd concentrated on it. I've got a 4, 5 pair in this. Oh no, look, I've got a 5 here. So that's a 4, that's a 5, that's a 4, that's a 5. This is no longer 4 or 5. Right, so oh, no, that's okay still. This has got to be a 1, 2 or a 3 by Sudoku. And this isn't in the same region as this, the grey 1, 2, 3 triple in this 15 sum here. So do I know what this green sum, well, I know it's 15, I do know that. Do I know what it's got in it? It's got a 7 in it in this row, because I haven't put 7 into any other cell. So it's got to be 7125 or 7134. I'm not sure if we know which of those is correct. It's definitely got a 1 in it, because its other 3 cells sum to 8. Okay, that's mildly interesting, look, for this domino, which now can't be 1, 7. And that's because I've got to put a 1 in those 5 cells, I've got to put a 1 in those 4 cells, and I've got to put a 1 in those 4 cells. And if you look very carefully, those cells I've just highlighted are all in 3 rows of the grid. So the 3 1s that must exist in those three rows, there aren't going to be more or less 1s in 3 rows. There's going to be 1 1 in this row, 1 1 in this row, and 1 1 in this row in the finished grid. So those 3 1s must be in these 13 cells. So I can't put 1 in there. Now this was adding up to 15, so this was adding up to 7. So this is not 1 6 now, but it could be 2 5, but only in one order, only in that order. But unfortunately, I think it can be 3. No, if it's 3 4, it has to be in this order. So this is quite restricted now. I've almost got sort of triples and quadruples in column 5. Okay, and now look, if we look along this row, I've not managed to put 6 into it yet, and 6 can't go in here. So that is a 6 by Sudokuage. So this is this green? Is that what we're supposed to appreciate here? Does this have to be green? Those 2 cells, at least, are in the same region. I'll make that region red. But red could be green. We've got to remember this. So if this was a 2-cell string before we exited the region, this cell would have to be a 9. And that, unfortunately, looks possible. If it's a 3-cell region, then it is green, because green will be locked in by it. So if this is 3 or more cells, all of these join together in a 7-cell region. So, right, so if that was the case, if we do make this red, and then we say that red and green are forced now to be the same, then we've got 15 here and 15 here. So we can't take another cell. This cannot also be red. Because if this was also red, we wouldn't have left this region in that sequential contiguous string of digits. So these 4 cells would sum to 15, and then we'd have to have a solitary red somewhere else that summed to 15 on its own, and that's nonsense. So what we need now, if we do this, is we need something that's impossible, I want to say. Because we know that the 2 missing digits from this region, this 7-cell region now, add to 15. So they're either 6, 9, which they can't be because there's already a 6 in the region, or they're 7, 8, which they can't be because there's already a 7 in the region. So I don't think this is possible. I think that this is not... no, hang on. I was going to say that, well, I think this is not red, but that might not mean that red isn't green. This is confusing me. So I'm convinced that this cell is not red, because that transforms red into green. And that we've just shown is impossible. But so this is a 2-cell string. Of that we are convinced, which means this is a 9. That's still some progress. But do we know that this is red, or do we know whether red is green still, or do we not know that? It could be, because we haven't got a 6 or a 9 in that string of digits. I'm not sure. Well, this is not red, but this is so confusing, this top bit, because at the moment we're in a position where green and red could be the same. But this cell is definitely not red, but could still be green if this isn't green. Or no, if that is green. Oh god. No, this obviously can't be green if this is green. But this is different from red, so I'm going to use blue now, just because I want to indicate this cell is very peculiar, and that must be in the same region as the peculiar cell here. But this could all be green, or either all of this. No, hang on. Either this is green, or this is green and this is not green. So do I now ask that question again then? Yeah, this doesn't work, does it? If this is now blue, surely red is now trapped. And what I mean by that is whether red is red or whether red is green, red has still some growing to do. And red is not in blue, because we've proved that, because the region sum line needs to have a boundary here. So if blue did take this cell here, red is trapped, and whether it picks up green or not, it's still not reached its 9-cell quorum. So I think that cell is not blue, which means that if that cell is not blue, this 2-cell sum is summing up to 15, and it's not 7, 8. So this is 6, 9, and there's a 9 here. So I think this is 9 and this is 6. Now the only bad thing about this is that it still has the opportunity to be green, because we haven't got 9 or 6 in green, as we established when we had 9 or 6 in red. Oh. So, no, I know what we do now. Now we say that red has to grow. Whether red is green or whether red is not green, red is going to have to keep growing. So that is red, which means this is red. Because if that's red, red has to reach 15 in this line segment. And that's not enough, because if this is a 2-cell sum, it can't be 8, 7. And it can't be 6, 9, because this can't be 6, 9, and that can't be 8, 7. So that is also red. So red has now reached a size of 5, which doesn't prevent it yet from being green, because that would create a 9-cell region. And actually, that's probably right, isn't it? Because that's 15, and that'll be the end of it with 15 there. The alternative to that is that green is blue, and then we'll have to find another 3 cells. But we couldn't we'd have to have 3 cells. And they'd either all have to be off the line, wouldn't they? Or they'd all have to be on the line. Because we can't split 3 cells into 2 lots of 15. I'm just wondering about how easy that is to do. Because how do I attach something to this putative region? If I say that blue and green are the same, and I have to add 3 more cells to this that contain, they're going to have an 8 in them, that's for sure. Because there can't be an 8 in here. And that's not even easy to do. But more to the point, how do I can't have 3 line segments attaching to this region, because we know that blue is different from red, so I can't take this cell, and no other cell that's orthogonally connected to this region is on the line. So I'm going to have to take a non-line cell. Now the moment I do that, I can't then go onto the line again. So if I took this one and then say, oh, now I can get on the line, that won't work, because these 2 cells will have to add up to 15, and they can't be 9, 6, and they can't be 7, 8, because they've already gone in the region. So I will have to stay off the line. And the only way of doing that would be these 3 cells without cutting yellow off. So this is the question, I think. Are those 3 squares, is it possible those 3 squares are in this sort of region? 1, 2, 3. That is a 9-cell region. And the answer to that is I don't know. That might be possible, actually, which is very irritating. I thought we were going in the right direction there. I can't see another way to take the 3 extra cells, because if I take those 3, I've cut off yellow. So literally it would have to be that one, and that one. That's the only way of making this region work. And then that would force these cells to all be 1, 2, 3, 4, 5, 6, 7, 8, 9. That would force the red region to look like that. Ah, maybe I can do something with 9s to disprove this. 9 is not there by Sudoku. So 9 sits in the corner of grey. Oh no, that's no good. That's no good. What I wanted was a 9 down here. So then I could have argued 9 wasn't in red and I would have got the right answer. So this column's got 1, 2, 3 left to place. That's not a 1. Do we know what this means for this region? No, and in fact I don't even know whether this is a 3-cell segment or a 4-cell segment, so I can't be sure about that. Although if it was a 4-cell segment, that would be red. And then these 2 would have to be red, and I don't think I'm getting to the right count then at all, because these are too low. There is a lot of constraint here, but I think the issue I'm having is how to solve this elegantly at this point. I don't want to sort of brute force it. I suspect there's something very pretty here. Okay, so alright, let's go back to Sudoku. I've got 3s and 4s to place in this row, and that's a 3 there, so that's a 3, that's a 4, which means that's a 5, and that's a 2. That's progress. Okay, so that might be what we were meant to do next. Now I've got 5s can come out of these cells, 3s can come out of these cells, 2 can come out of this cell. This cell's getting very restricted all of a sudden. What about this row? I need 1s, 3s and 4s. So this is a 1, 3 or a 4. Can't quite see how to do it still. I just can't see how to do it. Okay, let's go back to... Did I look at this earlier? I think I did look at this earlier because I noticed that those added up to 30. And therefore, if the next digit is on the line in orange, we've got to have all of the orange digits on the line, haven't we? So if we come this way, we've got to have a contiguous sequence that's going to have 2, 3, 4 and 6 on it, adding up to 15, bringing orange's total up to 45. But if we come this way, we have to stay off the line all the way, because if we do venture onto the line, we won't be able to make the remaining digits in orange add up to 15 if we've had one that's off the line. Oh, right. So it's this. This is straightforward. Yeah. Okay. So look, how could orange take this cell? That's the question. Because once it takes this cell, it must stay off the line. It can't take the 1. There's already a 1 here. So it's got to wend its way this way. Can't go back on a line, so it has to take that cell. Now, unless I'm mistaken, yellow is very much trapped in now. Yes, and yellow and orange are different. We've got this region boundary here. So this is wrong. This is definitely wrong. So that tells us that orange comes this way, takes a line cell. Therefore, all 4 of the remaining, well, all 3 now of the remaining orange digits are on the line. And orange can't be the same as green, so this is orange. Now it could take all of these, and that would force green to come out this way. Oh no, hang on, I looked at this earlier, didn't we? Didn't we look at whether green could take this cell? 1, 2, 3, 4, 5. If green does take this cell, if this is green, then green has a 5-cell string on it, uninterrupted 5-cell string on the line, which would have to be 1, 2, 3, 4, 5. And that doesn't work because we have too many 1s, 2s, 3s, 4s and 5s in this column. We'd make that Schrödinger cell. I remember we did that earlier. Sorry, this is all a bit disjointed because it's been so many hours since I looked at this. But that means that cell's got to be orange. Now, does it mean this cell? Yes. Oh, this was easy. Oh, Simon, this was easy. The easy way to do it is to notice that once this is orange, orange can't take this cell, because obviously there is a border there, and there's already a 1 in orange. So I've just found a very complicated way of proving that these 2 cells were in orange, and they're a 4, 6 pair, and there's a 6 up here, so we actually get them all. 6, 4, 1, 2, 5. What's that doing? I don't know yet, but that feels quite exciting actually. That's not 5 anymore. So I've got a 3, 4 pair here. I can... Yes. This is a 3 or a 4. And we remember there's a 7 in green. 3 other cells in it add up to 8, so they're not 1, 2, 5 anymore, because that cell's a 3 or a 4. So that's not a 2. This is a 1 or a... Oh. Done it again. I'm so stupid. Look, I could have easily shown that was not a 2 by looking at the 2 in its row, but I managed to find it a different way. 1, 3, 4, 7. And okay, can I do better than that? I feel that's almost certainly I can. I've got a 1, 2, 3 triple there by the looks of things, which would say that's got to be 4 or 7 now. Oh no, come on. I don't know actually. I know what I can do. I can draw some borders in, make it seem like I'm making progress. Does the fact I know that green is now 1, 3, 4, 7 affect whether green can be red or not, or blue? Nearly does. If that was a 3, if this cell here was a 3, then we would know that green was not the same as red, which would be a huge deduction. Right, I think we carry on with Sudoku a bit now, because we have got lots of information. This is a 7, 9 pair. This is a 1, 5 pair. These 3 cells have to add up to 15. 1 plus 5 is 6. That needs a 9, not a 7. So 9 and 7 go in the grid. Don't seem to do anything in the rows, do they? This cell now is not green, because green has a 1 in it. It's probably yellow. Let me think about this. What colour is this as well? Is this yellow or is it green? Oh, bobbins, bobbins, I don't know. Maybe it's this 1, 2, 3 triple here. We need 4s, 5s, 8s, 4s, 5s, 7s and 8s into these cells. 4s, 5s, 7s, 8s. That's not 4. That's not 7. Okay, and I know those 3 add up to 15, don't I? Because I worked out we couldn't make this red without these becoming red and us getting the count wrong in red. So if this is a 2, these have to add up to 13, and they'd have to be 5, 8, because they couldn't be 6, 7 or 4, 9. And that might be possible. If this is 3, these have to add up to 12, and they can't be 3, 9, but they could be 4, 8. Or 5, 7. No, there's still a lot of flexibility in these digits, I think. Wow, wow. Okay, so we've got to think more, think harder. Where should we look for something else to think about? This digit is obviously in a 15 relationship with this digit and possibly more digits, but these two. The thing is, I don't know what colour to make these. They could be green. I'll make them purple just for the interim. These two are the same colour. And actually, no, I'm going to go further. Those 3 are the same colour because I've just noticed I've got 7 and 8 and 6 and 9 looking at that cell. So if this was a domino adding to 15, that would be impossible. So at least these 3 now are the same colour. So if these are not green, green is having to come way, way along the bottom of the grid. 4, 5, 6, 7. Then hit the line. It'll have to take 2 cells on the line. And that tells, maybe we can do maths on this. So we'd have 15 over here, 15 there, that's 30, 37 here. These would have to add up to 8. Oh, okay, maybe these 2 digits then. That's a 2, 3 pair I've just noticed. If these were adding up to 8, there'd have to be a 1 in them. That would have to be a 5. This would have to be 1, 3, 4. I don't believe it. I think that might work. I can't disprove that, I don't think. This would be 5. This would be 1, 3, 4. This would be 2. No, okay, that doesn't seem to be disprovable, at least not quickly. So how do we do this then? Yellow has to... What do we know about yellow? Yellow is the smallest region. We know it's not green. Do we know yellow isn't blue? The answer to that is unfortunately no. What digits are difficult here? What digits are difficult? I must have got almost all the 9s in the grid. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Oh, there's one in one of those 2 squares. That's 8. And there's going to be 1, I think, down here for 9. Which doesn't help me. Okay. How do we do this? Okay, let's think about this. Right, yellow needs a 1, doesn't it? Is that this? Is that where it's going to get its 1 from? It can't... How many 1s have I got in the grid? Not many actually, so I might have lots of options for where this can get a 1. No, actually I haven't got lots of options, because where are the 1s in the bottom of this grid? Well, this yellow will have to get a 1 from the bottom 3 rows. So it could get this one. It can't get the green one, because if I join... There's no... Well, 4, 5, 6, 7. That would imply I could get from green to yellow in 2 cells. I can't do that. So it's not that. And the only other one in the bottom 3 rows is over here. And can... That might be possible. Actually, 4, 5, 6, 7, 8, 9. No. No, there is no way. That's 10 cells. Right, so that's yellow. We can conclude that. And now if that's yellow, it must join up like this, because we can't fit a region in the gap. So has that helped us? Is the next question. Right, one question we could ask now is purple yellow? That's an interesting question, because that would complete yellow if that was true. We'd have 15 here, 15 here, so we'd have to have 14 into these 2 squares, which would have to not be 6, 8. This would have to be 5, 9, which it couldn't be. So actually, this is important. There is a boundary between those. Now that must mean that yellow's going to have to... Is yellow going to have to hit blue? I'm not totally sure about that. How is it? I'm just trying to see if there's a clean and quick way of resolving this. I don't want to brute force it. There. I suspect there's loads of Sudoku we can do as well that will probably tidy this up, but let me think about this. So we've got lots of quite well formed regions now. So surely, right, if purple was not green, what is purple if it can't be yellow? That's an interesting question. How many regions have we got in the puzzle? 1, 2, 3, 4, 5, 6, 7, 8, and where is the 9th? Which one do we count as the legitimate 9th region that we know is not part of anything that we've already just put a highlighted cell in? That's tricky, because unfortunately green could be blue, so that wouldn't be legitimate to say blue is a new region. Green could be red, so it's not legitimate, you know what I mean, it's not legitimate to say red is a new region. Right, I'm going to do this in a slightly strange way then. I'm going to say that cell there in the corner. That cell is definitely not in any of the regions I've just put a highlighted cell in. There is no way you can get from any of these regions to here without in only 9 cells. It's impossible. If green wants to try and get there, it's either got to come through red, which is 5 cells, and therefore it can't take this, or it's got to come through here, and it's never getting to here because there's going to be a red region of 9 cells blocking it off. So this is the 9th region. So that means, right, this is very interesting. So now let's come back to thinking about purple. I'm not going to get rid of these highlighted points for a moment. Purple either joins green, and I think that's what it's going to have to do, or it can't join yellow. It definitely can't join green up here because that's going to be more than 9 cells. Or it joins with this digit here. Now, if this and this were in the same region, how on earth does green get to be 9 cells? 1, 2, 3, 4, 5 would have to be the only way it could do it without blocking off purple. And now purple, in order to get to this cell, would have to come through red. And it's too big then. So in fact, we have now proved, I think, that green is the same as purple, if you're ever in any doubt about that. And that means, but of course green could keep growing. We must bear in mind that. Green doesn't necessarily have to, although Oh no, actually, yeah, it could keep going. But now, what is that cell part of then? This is an interesting question. Because this is now not green. If this is green, those two are green, and green has 10 cells in it. So this has to be part of a different region. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's not part of yellow, and it's not part of green up here. 1, 2, 3, 4. Oh, maybe it is. 5, 6, 7, 8, 9, 10. No, it's not. Only just though. 6, 7, 8, 9. Yeah. Okay, so this is part of this. And once this is part of this, that is a 5-cell region. And this is so beautiful. Isn't it so beautiful? I'll get rid of the black region in a moment because I think it's about to collapse into other regions. But this is absolutely critical because once we've proved that there is a region across the bottom of 5 cells large, this region is not red. So red has to find a different home. How on earth can red not now be green? It must be. Because red is different from blue. Red clearly can't join another 6-cell region over here. So red's only option now is to become green. So if you are ever in any doubt about the redness and greenness of the puzzle, you have now had that all dealt with. So that is all forced to be a region. Now I'll change the bottom region here into red. That's red because otherwise it's a 1-cell region. We've got a 6-cell region here now. We've got presumably, oh no, blue could be red now. Still it resists. But let's do some Sudoku. That might be the easiest way to go forward because now I've got a 3 in green, so that's become 2. These two have to add up to 13. They must therefore be 5 and 8, which unfortunately it doesn't do anything. Well, it gets rid of, I suppose it makes that cell a 4 actually, which makes that cell a 7, so I'm aligning it up a little bit unfairly. Okay, 2 must be in that domino at the top, so that's not a 2. I've now got a 1, 3, 4 triple in column 7, so that's not 1 or 4. So 2, 5, 7 and 8 down here, which is probably resolvable somehow. Come on, crack. Okay. And still it resists. Alright. What's this? Why can't I see how to do this? I can't actually. I'm sure there's something simple now. There must be. It's almost. I've almost filled in all the digits. I haven't though got all the regions, have I? I suppose that's the thing I've not done. So at the moment, red is of size 4. So where's this digit? That's yellow, isn't it? Because it can't be green. Green can't get there. And if it was red, we'd be hiving off a 3-cell region. So that's yellow, which is a 7th yellow cell. So I bet yellow's going to take this 6-9 pair. That feels very likely to me. What digits has yellow got to add to its quota? It's got to add 3, 6, 7 and 9. This is a naked single then. Because of what yellow needs. Yellow needs 3, 6, 7 and 9. 6, 7, 9 there, so that's a 3. Which means that's a 2. That might be important. 4, 5 and 8 in the column. And this is not 4. Does that help us? Okay, let's look at this row. 5, 7 and 8 to play. That's a naked single. That's a 7. Oh, this is nice. So where does 5 go in this row? It's got to go here. That's got to be 8. This has got to be 8. That's not 8 anymore. 8 can't... Oh, yeah, that's great. That's great. 8 can't repeat in yellow. So now how does yellow escape? It must turn into, you've guessed it, blue. So these become yellow. This is that completes the yellow region, which is rather a strange looking region. This 8... 1, 2, 3, 4, 5, 6, 7. Oh, okay, it might be possible for this to be green. I'm not sure. 2, 3, 4, 5. No, it might actually be possible. Okay, so, but this 8 is doing some Sudoku-age for us. 8 and 7 go in the grid. This 8 is taking some 8s out from down here. Do we get to know what this digit is? This has to add up to 15. Or we've got to grow it again. Either would be interesting to know, wouldn't it? So, if we're trying to make these 3 add up to 15, 6 won't work here. Neither will 7, because that would require 8. So this could not be a 4. So this would have to be 5. It doesn't work. There's no combination that works here, I don't think. I'm just going to double check this. If we're trying to make this a 3-cell sum to 15, we could go 4 and 2, we'd need 9. 4 and 3, we'd need 8. 5 and 2, we'd need 8. Or 5 and 3, and we'd need 7. And all are ruled out. So green must go again. And now this cell can't be green and must be red. And now 1, 2, so we've got one more. Oh, yeah. And what's missing from green now? We've got 15 here, that's 30, and a 7, 37. The other cell must be an 8, so it can't be this one, it must be that one. This is, I mean, even now it's giving some absolutely beautiful logic, isn't it? And that must be therefore the last red cell. And that is therefore the pattern of the regions. And it should now simply, I say simply with a great deal of sarcasm, be a case of filling in the Sudoku. Those are a 1, 3 pair, so that has to be a 2. That's a 3. That's a 3. That's a 1. That's a 1. That's a 5. That's a 4. That's a 5. That's a 2. Actually, this is going better than I expected. Can we keep that going? Yes. 5, 7, 3, 2, 1, 3, 4, 1, 9. 1, 3 pair. Yeah, that's done. 3, 1, 3, 4. Now what do we need here? We need 6s and 9s. Yeah, we can do that. 6, 9. This digit here is now a something. Why can't I see what it is? It's a 6. And this digit here should be a 2. Now let's double check this. This should now add to 15 and does, so that looks very good. So not only is the Sudoku working, but the line is working. That 654 is 15 as well. What a brilliant puzzle. Woofers for gig. Happy birthday, my friend. And thank you, really, for giving me a present on your birthday, which seems absolutely unfair. But that was quite magnificent. Jacob and Woofers for Gig should be taking a massive bow, because this puzzle is not only original, it is brilliant. It is very brilliant. And I hope that's the right answer. I don't know if the software did understand it. It says I did it in 86 minutes, which is a total lie. I don't know why it thinks that, because obviously it's been... Well, what time is it now? It's now 5:45, and I started the puzzle at about 10:30. So it's been a lot longer than 86 minutes. But anyway, that's what the software says. Computer says 86 minutes. Fantastic. I hope you enjoyed it. Let me know in the comments how you got on. It's another long video today, which I hope you'll forgive me for. And we'll be back later with another edition of Cracking the Cryptic.